Welcome to Blackhat USA 2010. You are in the final installment of the cloud virtualization track.
Yeah. Hello, my name is Georg Wicherski, and I'm a virus analyst with Kaspersky, the antivirus company. And today I will be talking about Dirtbox, which is a very scalable x86 and Windows emulation approach that I created because I wasn't very confident and happy with what was out there already. So what I will be presenting on today is not really related to my day job at Kaspersky, but related to my bachelor thesis I'm currently writing. So all the stuff I'm going to be disclosing today will not help you evading emulators of Kaspersky or whatever, but I'm kind of porting ideas to the Kaspersky job as well. But anyway, let's first find out why not just use these existing solutions and, well, how this looks in general from a high-level point of view. So there's two different kinds of sandboxes out there. First, there's malware analysis sandbox solutions that will just ease your job as an analyst by automatically analyzing malicious code for you. I categorize a lot of them to what I call VMware rootkits, like CW Sandbox, JoBox, Thatbox, and these kind of sandboxes. Of course, they don't need to be run inside VMware. They can be run on the physical computer, what they call bare metal sandboxes. But the thing here is that for ease of use, and also you don't want to install physical computers all the time, most people just run them inside VMware and use the snapshot features to reset the sandboxes. So that's why I call them VMware rootkits, because they're just a Ring 0 driver that records stuff. Then there's the other kind of sandboxes, like Norman Sandbox, for example. Norman Sandbox uses Norman's custom x86 emulator. Or Anubis, for example, which is actually a modification of QEMU and therefore has some virtual machine view from the outside. But all they have in common is that they are using a full operating system like Windows inside some virtual machine, except for Norman Sandbox, which really only emulates userland code. So Norman Sandbox is more related to antivirus in any way either. So the thing is, that doesn't really scale up because you can only analyze one malware sample and one real Windows virtual machine at a time. And Windows virtual machines, at least for XP, they need at least 512 megabytes to really work. So if you have a lot of malware samples to analyze, like for example Shadow Server Foundation, who gets a lot of samples each day, you will need a lot of physical systems to scale up your sandboxing. So Shadow Server Foundation, for example, has more than 500 physical machines each running multiple virtual machines to scale up for their malware analysis, and they're still building up some queue. So that doesn't really scale well. That's one of the drawbacks. And the other one is, of course, detectability, because I mean, at least for the public web interfaces, these whole system emulations, they have like a computer name, they have a desktop background color, stuff like this. So what malware developers usually do is they just add some code to check for specific computer names or whatever, and thereby evade all these analysis sandboxes very trivially. Of course, if you set up them on your own, you can change the desktop color and the virtual machine and everything like this, and then you will not be as easily detectable, but still there's very easy ways to detect it. And then again, if you are running inside VMware, there's obviously a lot of malware which does not run in virtual machines, and you will not detect that at all. The other kind of emulators for malware is malware detection emulators. They don't aim at really understanding what a malware sample would do at all, but they're mostly there for just detecting if it's malware or not. And most serious antivirus solutions these days, they have one of these emulators inside. So the picture here is from a ROC AV. That's not really a serious antivirus solution. But the thing is that they're working on an API level emulation. So they're mostly doing software emulation. The whole x86 instruction set has been implemented as C++ code. So they're just interpreting the code in software, which is very slow. And then they emulate the environment, the Windows environment, at API level. So as soon as there's a call to an API in kernel 32 or users 32 or whatever, their emulation code of the Windows environment kicks in. And that's very detectable. For example, what you can do is unimplemented APIs, because every single API that is there in the Windows world needs to be implemented by the antivirus emulator too. You can look at the heap layout. I will show some more stuff later. So in essence, they have the drawback that they're usually slow, which is okay because you just want to detect malware and don't want to do complete run, but just run through some unpacking or whatever. And then, yeah, easily detectable. I mean, people are doing this arms race thing, so antivirus vendors, they patch the emulators. Once they see new malware samples detecting the emulators, then the malware authors again change the detection, and yeah. But that's not really something very good, I think. So one example for detection is side effects of APIs. So some of you probably know structured exception handling. What is that is if you have a try statement, try and catch statement in Visual Studio C++, they all share common code if you do these constructs in C++. So the compiler then generates code for this function, and the function epilogue is always the same bytecode. And this epilogue uses a sequence of push ECX and then return to the calling function. So that means that with this code in place, you always will have some detection of the ECX register, because the ECX register, it's by calling convention, belongs to the called function. So that means the contents of the register are undefined upon function return, and well, real-world code shouldn't care about the register value. If it uses the register itself, then it should push it and then pop it before the API call to save the value in it. But the thing is, because there's this fixed bytecode, push ECX and return, in all these SEH protected functions, it's possible to predict the value in ECX register, for example. And that means you will always find the value of the end, the address of the end of the protected function inside the ECX register. So this can be predicted, this address, for example, by looking at the code in memory and scanning for return instructions or something like this. And then you can just, upon API return, compare the expected value of the ECX register with that address you found in memory. And if they're not the same, then you probably are running inside an antivirus emulator, because the antivirus emulator, it will not execute all the bytecode that it has there in memory, but instead it will have some custom implementation of this API, and that won't, of course, set these undefined registers. So this breaks this simple trick, very simple trick, implementation-wise, that's like maybe at most 2 hours of work, breaks a lot of antivirus emulators right away and evades detection. There are some, if you look at different antivirus emulators, there are nice ways how they try to circumvent this ways of detection, but then again, it's also trivial to circumvent their circumvention in a way. Of course, using this could be used from a defense side, could be used for generic anti-emulation detection as well. So they're using an undefined register after an API call, which is suspicious behavior, but then again, compilers sometimes generate strange code, and actually for Kaspersky we looked into using this for generic detection of anti-emulation tricks, and we had too many false positives, because some strange compilers like Bolin, for example, they generate strange code that will, I mean, it will use, it will look up the values in these registers, never use them, but nevertheless access these undefined registers. So. And the whole detection thing, though, relies on the simple fact that all these antivirus emulators, they don't execute the API's bytecode itself, but they have a, so to speak, in the host system, an own implementation of the API. And if we can get around this limitation of not executing the API's bytecode, yeah, well, we won't be detectable by this. So what does the whole Dirtbox system like name Dirtbox come from? A colleague of mine was saying, "No, okay, your name for your project sucks. So you're doing a sandbox and there's dirt in there, and yeah, now you have a Dirtbox." Well, the idea behind this is that instead of emulating at the API call layer, the emulation is at the system call layer. So all the native code, bytecode of the APIs is actually run inside the virtual CPU. That means, for example, NTDLL and whatever is run inside the virtual CPU. And in essence, all these other DLLs and API implementation DLLs, they wrap around NTDLL, which at some point will issue a system call, and that's where our emulation kicks in. So this means that we only need to implement system calls, which is, I will talk a little bit more later, and then we've got everything covered. I mean, you can create as many DLLs wrapping around these system calls as you want, and new APIs and whatever, but still, at the end, either it's all happening, everything is happening inside the process itself, and then we don't need to emulate anything, and everything that would call out to the operating system goes to the system calls. So if we emulate as a system call layer, we get a lot of stuff for free, basically. And also, malware issuing system calls directly is also automatically supported. So if you're working on AV emulators and these people say, okay, this malware is issuing system calls directly and whatever, they're usually just adding signature-based detection for it, and that's it. So the general flow, as you can see here, is execution starts inside Dirtbox, and there's these two components, Dirtbox and libcpu. Libcpu is the virtualization / emulation of the guest code, of the malware code, and Dirtbox is the Windows kernel emulation layer. So you have inside the libcpu, in the guest memory, you have your malware sample and TDLL, for example, and all these other DLLs it's using for APIs. And then you have this separation, which is a system call, basically, which would be the transition to ring 0 in a real system, and in this case, it's a transition to Dirtbox. So we emulate the system call, and then we hand back execution after the system call back to to libcpu, and then we execute bytecode. So it's never-ending cycle until we reach the end of the process or whatever. So the first part is libcpu. I did a custom x86 virtualization / emulation because there's different solutions out there, but I wasn't really happy to use them for this project, so I just wrote my own. Well, as I've said, software emulation of x86 bytecode is too slow because, I mean, it's already slow for these AV emulators that run at API level, but in this case, we're executing even more bytecode because we're executing all these DLLs too. So executing a lot of bytecode requires a fast solution. Other existing virtualization solutions like QEMU or BOSS are too powerful. They do too much because we're only interested in running hostile ring 3 code. But all these existing virtualization solutions, they allow you running ring 0 code too, right? Because they support full operating systems, and we don't need that. So they have their own memory management unit. They have support for privileged instructions like ports and whatever, and we don't need all that. And because we don't need this, we can cut out a lot of stuff and therefore be just more performant because we don't support it. But on the other hand, we want instruction level introspection for analysis reasons. So we cannot just use, I don't know, VMware or whatever because we want to see every single instructions in some cases for more fine-grained analysis than just recording API calls like CW Sandbox would do. So I did my own stuff based on LDT. This is pretty low-level hacking stuff, but therefore it made me gain a lot of performance boost, and yeah, just gonna explain it. So what you need to know first about this is x86 memory views. When you're talking about x86 and memory views, people usually know that there's physical address space and virtual address space. And physical address space is really like the physical random access memory you have inside your computer, and it's all separated into so-called pages, usually 4 kilobytes, sometimes 4 megabyte big. And then there's a mapping from the virtual address space, which is what you see as a developer or whatever, to the physical address space, which is called paging. And in paging, you can map these different pages, these different blocks to the same physical page, for example. So you can save address memory if you're having the same process launched twice and stuff like this. But most people in reverse engineering are familiar with these concepts, but in reality there's not only those two, but a third thing which is called the logical memory view, which is also part of the protected mode concept. And well, logical memory view comes from segmentation. So a logical memory view to virtual memory view mapping is not as fine-grained as the paging mechanisms, but it only allows you to map segments or certain size blocks. So what you can do is you take like a segment and say, okay, the segment starts at this virtual memory address and is that many bytes big. And that allows you to, from the virtual address space, extract blocks of a certain length. Well, why does nobody know about this? Because on the current operating system it looks like this. They do have segmentation and they use segments, but what they do is basically for all your code and data, they create one segment which starts at address 0 and is for 32-bit address space, it's 4 gigabytes big. So they take the whole virtual address space and they just put it into one logical address space segment. So that's why people usually don't see that. But what we're going to do is actually we're going to use this feature to create our guest memory isolation very efficiently. So yeah. The segmentation itself on the operating system is implemented by two tables, the global descriptor table, which is allocated by the operating system and shared among all processes. These are on a normal operating system these days, these are these general large segments, and yeah, that's why nobody cares about this. And there's the local descriptor table, which is process specific, and because it's a privileged stuff, it has to be allocated by the operating system too, but operating systems like Linux offer system calls sysmodify LT, or Windows NT offers NT set LT entries, which allow you to specify your own segments. Of course, they do some filtering on the segments you create, because otherwise you could do very nasty stuff like ring zero code execution with these segments. But they allow you to have some control. And this descriptor table is process specific, and for most processes is usually not present. And it's a very, very unknown and very little used feature, but software like Wine uses it. Some old patches that before there was a non-executable bit, there was already for Linux non-executable stacks that use the local descriptor table too, stuff like this. So what I'm doing for this Dirtbox thing is we have in Windows 32-bit Windows, we have 2 gigabytes of continuous user land memory. So for executing our malware, we create a segment which is 2 gigabytes big, and that's our new guest memory. And that's a very nice thing, because on Linux, by default, you have 3 gigabytes user space memory, so we can stay totally in the user space and have the Windows user space inside there too. Well, the thing is though that sometimes, depending on your process layout, on 32-bit kernels you have only these 3 gigabyte, and sometimes depending on where your heap is located, if ASLR is on and so on, you cannot find 2 gigabytes of continuous address space. But on 64-bit kernels, you will, even for the 32-bit processors, you will always have the full 4 gigabyte of address space, so it at least works there. So instead of writing my own stuff for memory management, I'm abusing the existing hardware with some tricks to do the stuff for me. That saves me time for development effort and also gives me speed increase. So the code itself, the rock code, is being executed on the host CPU with some limitations. And we don't need to do instruction rewriting like QEMU does, for example, or VMware does in some cases, if there's no hardware virtualization extensions. Because we are using the host MMU with segmentation to do the whole memory access isolation for us. And since we don't need to do any instruction rewriting, we have a lot of performance boost because we can execute the code in place instead of copying and rewriting it. We don't need the time for reassembling the rewritten stuff, generating this code, and so on. And yeah, so we're taking these basic blocks and executing them on a host CPU. So what do I mean by basic block? Well, basically basic blocks are the stuff, the boxes in the EDA graph view that are connected with arrows. So a basic block formally is a sequential flow of instructions that are terminated by either control flow modifying instructions such as return, call, jump, conditional jumps, and so on, or privilege instructions like syscall, sysenter, in, out, if you see them in user land for some weird reason, and so on. And always I extract always one of these basic blocks, put them on the host CPU, execute them there in this isolated environment, and then continue at the next basic block, analyze it again, and put it there. One exception is there's backward pointing jumps. So if you have like a basic block which contains a conditional jump or unconditional jump that points back into the same basic block, by definition this would be like to the place where it points back. This would now split this basic block up into 2 basic blocks. But I ignore that, because if we just jump back into this code and we don't create additional basic block, we again have some performance improvements for loops and stuff like this. So if there is a backward pointing jump into the same block we're currently analyzing, we just directly copy the whole thing instead of adding an additional basic blocks. So loops are very fast, at least small loops that are not very complicated. And currently, with the current implementation, I don't implement any code caching because, well, I don't do instruction rewriting. So the execution of a basic block doesn't require a lot of analysis code. And therefore, there isn't a huge benefit from code caching. The only thing you could really cache is the length of the basic block you determined just. But yeah, that's just an integer. And I mean, I should try it out maybe, but I don't think I will have a lot of performance enhancement from that. So how are we handling self-modifying code? It's very trivial. I mean, self-modifying code, of course, could mess around with that in case it would rewrite the same basic block we're currently executing, because it could insert some control flow modifying instructions or whatever that would have terminated the basic block during analysis. The very simple solution is, before executing actually the code, I'm protecting the currently executing page to be non-writable. So as soon as there's self-modifying code which tries to modify exactly inside the same page, a segmentation fault will be generated by the host operating system. I can catch that, and from there on then start single stepping through the code, and then therefore allowing self-modifying code. Thing here is, though, that this is a very rare case, because with most self-modifying code like packers or whatever, they're usually not writing or generating code inside the same section a lot. I mean, they're doing this a little bit for debugger evasion, analysis evasion, and stuff like this, but the most of the unpacking stuff then happens into different sections, which is different pages, so there's not allowed. I mean, segmentation faults are expensive, but this doesn't happen very often. So that's, again, a very cheap, hacky way to avoid development time, but it works and it's very performant. So I'm going to show you a little bit demo of this libcpu things. This is just some generic instruction stuff. So what I have here is a very, very simple test case code. It's just like a shell code, so there's no real binary format here, just a binary data. This is a very simple code. It initializes the ECX register with a lot of iterations. It zeroes out the EAX register, and then in the loop itself, which you can see at the label called 1, it increments EAX, decrement ECX, and as long as ECX is not 0, it jumps back to the loop start. So it's a very stupid loop that just counts up the one register, counts down the other one, and then we end with an interrupt 3. So you would expect in the emulation environment to take this a lot of time, but yeah, it's very fast. And why is that? Well, this is the debug output here. So as I've said before, backward pointing jumps are always not considered to terminate the currently executing basic block. So what you can see here is that everything, the whole code there is considered to be one basic block, and the whole code is put directly on the host CPU and executed there in place. So the only second basic block is a terminating in 3 instruction. And as you can see from the register dumps here, initially, well, at the end at least, EAX is the desired iteration counter, so we really incremented each time, and I didn't cheat you. So if you run some timing on this, this is quite fast. It takes, no time, if you can believe this. As a comparison, I took libemu, which is libemu is a very nice library for shellcode detection. You can use it for client-side honeypots, server-side honeypots, that kind of stuff. But libemu is, which is by the way open source, is a full software emulator. And that means it's kind of slow. I mean, this is now, of course, comparing, in German we say like comparing peas with apples, because, yeah, it's not unfair to compare a virtualization with software emulation. But just so you get an idea, I'll first add some verbose output, so you can really see it does all the incrementation and whatever. But printing stuff is, of course, slow, so I will leave that out. But executing it, you will see that it takes a lot of time. And, okay, yeah, it doesn't take, oh, well, it did take some time, at least, comparably longer. And I've been benchmarking this with different iteration counts. Obviously, this is a linear difference, and it's about, depending on how much iterations you do, 1,000 to 5,000 times slower. So libemu, I chose libemu because it's open source and you can verify the results. But basically, all the antivirus emulators will suffer from the same deficiencies. So if you have like some crypto puzzles or whatever in your packer, it's very easy to evade antivirus emulators. The other demonstration of libcpu is a little bit more complicated. Well, let's say shellcode or test case. Initially, we initialized the EBX register, which we use as a counter with 3, and we reserve some space on the stack. And then we use fnob and fnstore environment to store the floating point environment, which also includes the address of the last floating point instruction executed. So this combination of these 3 instructions there basically just gets me the value of the address of this point here, of this label, into the ESI register, where we will start copying from. Then I also copy the source register to the target register, add, of course, the length of this code block here, of the code block from sled to end, and then I execute repeat move single byte. So basically, it's just like kind of a mem copy. So this code copies itself right after itself, and well, then it decrements EBX and then jumps back. Well, if it reaches 0, it jumps to the end. No, if it's not reached 0, it jumps to the end, and at this label end, of course, there will be the copy of the code we just generated. So this code is kind of a copy sled because it always copies itself after each other. And after 3 iterations, we will reach the N3 instruction finally. Okay, well, as you can see, it worked. Well, this is self-modifying code, so let's scroll a little bit up. So initially here, what you see here is a move EBX3 and so on, the initialization, and then the get PC and so on. And at some point, we put this whole basic block, including the rep move single byte and so on the host CPU. What you will see then is guest signal 11, which is segmentation fault at address 1E. And 1E is the address. No, sorry, this is the default address, but EIP points to 18, which is the repeat move single byte instruction. So that is because it's writing to the same code page as what I've been explaining before, self-modifying code. It generates this fault. So we go into single step mode, execute only the rep move single byte without protecting the page as described before. And this allows us now to copy the code. And after this, we continue the basic block. In this case, it only contains the decrement EBX instruction. Then we're reaching the jump if not 0 instruction, which needs to be emulated in software because it's control flow modifying. And then if you look now at EIP, we're just copied ourselves after each other. That is where some of the end was located before. We execute the same basic block again and the sepals for 3 times. And yeah, after some time, we will reach the N3 instruction. And if you look at the EIP value, this is way beyond the place where it initially was because we copied each other all the time. So this is how self-modifying code is supported. Okay, so much so far. So one thing I said before, libemu is very nice for shellcode detection and everything, but it's very slow. I created libsizzle, which is, well, I could have called it libx86 shellcode detection or whatever, but that's quite long. And names like libshellcode, libsc are all already taken, so that's what I decided to name it. So what does it do? Well, it's also for shellcode detection, and it's a very, very simple approach. We brute force over the byte buffer. So libemu, because it's slow, has very nice heuristics to find out where there could be a possible shellcode start and so on. But we don't need that because we have very high performance, so we can just put all the byte buffer. And we try some offsets in this byte buffer, and if from a certain offset, executing from there, we can execute n-valid instructions. We assume we found a valid shellcode, because for non-shellcode, which is not really code, you will not be able to execute a lot of instructions because you will run into segmentations faults or something like this. And in reality, I had to add some more nice heuristic, like count of basic blocks executed, number of interrupts executed, and stuff like this. But it's not really very fancy. So in essence, you just brute force over it, try to execute it from every single byte offset. And to improve performance, I pre-filtered buffers. So I'm scanning for so-called get PC sequences. These are like little gadgets, like what I've showed before with the floating point unit, that get the address of the code, the value of the program counter into some register. And we have 4 different candidates for these gadgets on the 32-bit x86 architecture that I'm scanning for. First 2 are opcodes 89 and A3. They are for moves that either move from a register to a memory location, or from EAX, which is just a different opcode to a memory location. And these are used for SEH, Structured Exception Handler, get PC gadgets on the Windows architecture. Then there, which is very generic instructions, but there's a certain prefix to them, which is for the FS segment. That's just some details, but you can filter out more of this. And then also there is the FSTNF instruction, which is used for the previous gadget I've shown you. And then, of course, you can use the call pop primitive for getting the instruction counter. And filtering for that already discards a lot of real word buffers because they're all non-ASCII opcodes, so you can filter out a lot of stuff already, and then again it's very fast if you do some additional parsing. So for these operands, for these instructions like the move instructions or the store floating point environment instruction, I actually also kind of parse or disassemble the operand and do try to find out, is it actually a valid operand? And if not, I can also discard this position in the buffer. So for the floating point instruction, I also require the operand to be relative to the ESP register because that's what you usually see. I mean, obviously there's ways to circumvent this, but this will catch all the real world shellcodes. And that's what I'm actually releasing for free on the internet. So if you go to the address there, just code.mlec.org/libsizzle, there is a free version. You can just use it as a dynamic library, and it's like a oracle for binary buffers. Is there shellcode in that or not? And that's very nice because you can just take like network info or whatever, throw it at it, and ask is there shellcode in it or not. Of course, it doesn't work for return-oriented programming approaches. It's really just only the text bytecode. But for example, for CTFs or whatever, this is really nice because there you usually see real shellcode. And then if you have detected shellcode and actually you want to know what does a shellcode do, there is the free shellcode emulator written by Markus Kötter and Paul Becher, libemu, which I've been talking about before, which can also tell you what would the shellcode actually do on a real system. So you can get there for free at the other address. So let's have a little demo of that. And that's really just a side project. I mean, as soon as you have like libcpu, like a virtualization solution, you can create so many other projects from that very easily. So let's first have a look at performance. I'm piping 16 megabytes of urandom input to it. And yeah, let's do it a second time so it can cache the data from the hard disk. So it in total takes 300 milliseconds to examine 16 megabytes for data. And of course, since this was urandom data, we did not find any shellcode in there. There's some segmentation faults occurring that were not expected. I'm filtering out stuff that is inside the basic blocks, and there's some strange segmentation faults also happening, but yeah, we're catching that here. So as you can see, it's quite performant, and if I would be doing it on 2 cores and not be running my presentation, VMware, Windows Virtual Machine, I can, on my laptop, catch up with 100 Mbit line speed of data. And if you do it on a commodity server with like 4 cores with like, I don't know, i5 or whatever, you can do it at 1 or 2 gigabit line speed. So you can really do this on live network streams and stuff like this, or you can also plug it into your honeypot solutions and whatever. Well, next example is, I've been testing this with various shellcodes. Initially, I was going to test this with like Metasploit shellcodes, but these are, quite known, and so what I ended up with is testing it from last year's DEF CON shellcodes, because there people wrote their custom shellcodes with custom encoders that weren't so easy to detect. And yeah, so we're running it here on some other buffer. Of course, this is now only some PCAP data, only 200 kilobytes, so it's a lot faster. So we end up having 34 different candidate offsets in there, and then we actually at one offset found the real shellcode after verifying it in the emulation. So if you look with the disassembler, what did we actually find there? Well, there was some knobs of first, some knobs obviously, and then it's some inc edx, sub ecx, ecx, so that's just some initialization of registers there. And then the interesting instruction is the F3 instruction you can see there. This is the floating point instruction. It's just a random floating point instruction they've been using, but this sets the instruction pointer for the FPU to that specific address. Then they initialize some loop counter there, and then there's the interesting gadget storing the floating point environment. So that's exactly what you would see in shellcode. And then what you see after it is like here they start a little loop, which would then decrypt the shellcode. So in each iteration they add 4, so they encrypt 1 double word at a time. And actually XOR here, and what looks like garbage here is actually already the XORed loop instruction. So if you do the math, if you add to this address, add 15, you will end up inside this instruction, and this is the first XOR here. So yeah, that's what they do. So it worked very well on that shellcode, which was XOR encrypted shellcode, and also if you have raw shellcode, which actually, funnily, in this case, if you have unencoded shellcode, it's a little bit harder to detect because you don't have these getPC gadgets. So I had for Linux shellcode to add yet another gadget, which is the int80 gadget. Obviously, a shellcode does system calls, and that works too. So what I did was I combined the urandom data and to the end appended some other shellcode during the CDF. And again, the urandom data takes some time, but it doesn't really generate any false positives. But then we have at the offset at the end, we actually do think that we have shellcode. So let's look at that. And well, it turns out it actually is shellcode. So why is my terminal fucked up there? Okay, there we go. Actually what you see here is they just zero out the ECX register, then they give it as a last parameter to the function they call. They load EAX with the system call number 6, and then invoke int80. And well, this is obviously not a Linux shellcode, but a FreeBSD shellcode. But still, they use int80 for invoking system calls on FreeBSD too, so we detect that shellcode very easily as well. And so this is very performant, it's very easy to implement, so yeah, nothing too cool, but as I've said, it's released for free, and it's very useful for intrusion detection stuff, or if you want to write honeypots, you need that, like if you want to write low interaction honeypots. Okay, so let's get to the essence of this talk, Dirtbox, or what I call the system call implementer Sisyphus tale, because, well, yeah, initially you're like, okay, there's thousands of APIs and only 1,000 system calls, but obviously 1,000 system calls is still a lot to implement, and yeah, system calls aren't really documented in the Windows world, so it involves a lot of reverse engineering of NTDLL and NTOS kernel and stuff like this. So it's a lot of work, but still. So why system call emulation? Well, I've already told you that I mean, API emulation is kind of weak in some regards, but still it's easier to implement, so why go through all the hassle? Well, there's some documentation actually out there. There's the Wine and Reactor OS source code, so they can already give you some pointers if you would be doing this on your own. And the other reason to do the system call emulation is we get a lot of genuine execution environment that really looks like on a real Windows system for free, because we're executing all the native code that would set up this environment on a real Windows system too. And then again, with all these APIs, there's really an unbound number of APIs. So there could be just some fancy DLL, and then you again have to add these API calls and so on. Whereas with system call numbers, you have well, it's quite a high limit, 1,000 system calls, but it's a fixed limit. And you know, if you would implement all of these, then you're definitely done. Instead, with API level emulation, you know, it's like this arms race you always see with malware. And there's the issue that, as I've said before, some malware directly issues system calls, like some viruses mostly, not the Trojans and Vectors you see, but all these really cool metamorphic viruses, they often use system calls directly. And we support that out of the box because that's what we do anyway. And we avoid all these API side effect detectability issues entirely. So I've been saying we get things for free. Well, what actually do we get things for free? I have 3 examples. There's more stuff we get for free, but just picking up 3 examples. We get PE parsing for free. If you have been doing some PE stuff, you will probably have noticed the PE format is very nicely documented by Microsoft. The only issue with the documentation is that it's not accurate in that sense that the Windows binary, the Windows PE loader behaves differently than this documentation. And also the PE format, it has some things where it's very easy to screw up. So if you do PE format fuzzing, you can find a lot of interesting bugs in like IDA and other software. So there's not easy to parse PE, even if a lot of tools support it. If you really dig into the file format and try to break some stuff, you can break a lot of tools very easily. But why do we get it for free on the Windows platform? So the process startup if you create a new process on the Windows, in the Windows, it's mostly handled by the new process and not by the kernel. So on Linux, for example, loading the binary is entirely done in the kernel, mapping everything. But in the Windows world, it's mostly done in userland, which was a surprise for me, at least when I looked at this the first time. So the step by step, it goes like you have always a process that tries to create a second process unless we first process in the system, but we're not doing booting anyway. So you will have a process calling the nt-create process system call, which allocates a new system, a new process in the structure in the kernel. And then the creating process will create a so-called section object inside the just created process, which means it basically maps the image and also ntdll into the new process. So this is what the kernel has to do. It requires that the kernel parses the section headers of these two PE files. But parsing section headers is not so difficult. There's way more difficult stuff in the PE format. So we just need to map the different sections into memory. And then the creating process will create a new thread with the on the entry point, with the entry point pointing to a place inside ntdll. So it does that with an asynchronous procedure call. And this specific execution point inside ntdll is called loader initialize func. The name already says it's the initialization of the process. So this point in ntdll would do the relocation of the image if necessary, resolving the imports, invoking the thread local storage callbacks, which are often used by malware for obfuscation, invoking DLL startup routines if it's a DLL, and so on. It will automatically do this for you, and we'll do some more magic, which I will show in the demo. So all this, more difficult parsing of the PE format is done by the ntdll bytecode, and we don't have to implement that our own. So all we have to do is implement nt-create section and nt-map view of section for these seg image sections. So it's really only parsing section headers. So there's already a lot of stuff we got for free, and well, if there's actually PE bugs inside there, then it wouldn't really run on the real Windows system, so we get a very genuine view of binaries. Whereas a lot of malware analysis tools and disassemblers and so on, sometimes they don't support stuff that would have worked on Windows, and sometimes they allow you to do stuff which actually wasn't allowed on real Windows systems. And there's really nice stuff you can do, which goes beyond the scope of this, but yeah. So second thing we get for free is a very accurate heap implementation. Because of API level emulation of these antivirus emulators, a lot of them have their own guest heap allocator, and they implement this in the emulator host. So because they're doing the heap implementation in the host, what you will see is that if you call malloc or RTL allocate heap or whatever, heap alloc, it will give you some address because, of course, they need to provide you memory management. But and on a real-world scenario, you do have like heap headers in front of these addresses, and most of these AVN emulators won't put these heap headers there, for example. Then again, on a real Windows system heap, you will have stuff like arena structures for heap and so on. And a lot of antivirus, some put heap headers there, some like fake heap headers, but these arena structure stuff like this, that is not put there by any antivirus emulator I've known. So it's very easy to, by looking at the heap, figure out that it's actually an antivirus emulator you're running in. Luckily for us, the Windows heap is implemented in ntdll too. So all the memory management is done in user mode as well, as we would expect probably. And all it does is interfacing the kernel with nt-virtual-alloc, nt-virtual-free, and so on. And these are page granular, so we don't have to do any heap blocks or whatever. We just care about allocating pages and freeing pages. And yeah, stuff like heap protections, like heap cookies and so on, are all handled in ntdll. So we got again a very genuine environment in that regard. So if you just want to fingerprint other emulators, just do a malloc of 0 byte size and look 8 bytes in front of that, and that will usually always already tell you you're running inside an NV emulator. Other issue would be if you want to have more advanced detection, deliberately overflow your own heap block, overwriting the heap cookie, and if you're free, the C block, see if there's an exception generated or not. And if there's no exception, then you're probably inside an AV emulator. And the third thing we get for free is proper structured exception handling. I mean, structured exception handling means that you have on the stack a linked list of exception handlers that are function pointers, basically, that will handle exceptions. And all we have to do is actually provide a context record, which is just basically a view of the current CPU state. So it's very easy to generate the contents of the structure for us. And then jump to inside the guest, of course, and TDL KI user exception dispatcher. So that is what the real kernel would do as well. And all of this handling of structured exception handling will be done by NTDLL for us again. So it will look up the current top of the SCH chain in the thread environment block, walk this list invoking these exception handlers with the correct flags, and especially invoking them twice, because you'll always have one run finding an exception handler that can handle the exception, and then there will be an unwinding run where where these functions will be called a second time with different flags. And a lot of AV emulators, they don't do the unwinding run, so if your function pointer gets only called once, you can detect this, you can look at the flags and so on. And also, actually, NTDLL, depending on the Windows version, of course, will check for safe SEH structures in your binary. So again, if you would have a safe SEH structure in your binary and then create a non-registered SEH handler on the stack, and you don't run into an exception when triggering, but instead your exception handler gets called, then again, you know you're in an antivirus emulator, because they don't care about safe SEH at all. So yeah, just link your binaries with your malware with safe SEH and deliberately trigger an exception to a non-registered SEH handler, and then check inside unhandled exception handler if stuff has been called or not, and if not, you're on a real environment. If it has been called actually your stuff, then you're in an antivirus emulator. But again, we get all this stuff for free from just executing the native bytecode. So I have a little bit demo of Dirtbox itself. Oops. So I have a very simple test case in this case. Just some binary I wrote in assembler. Basically, what it does is called tick count and so on, but it doesn't really matter, as I will show you now what it does. So we just start execution, and I've got this debugger-like command line interface to it. And what you see here is, of course, first some debug output from the section object implementation. So we're loading some section objects for NTDLL and the image we're actually executing, creating these section objects. And then we'll be calling the loader initialize function to actually start execution. Well, this function expects 3 parameters, and well, we can just provide some value for them to work. So then we run into libcpu, start execution, and the first thing that will happen is a system call to NT open key. So the first thing at all that's some of the magic I've been telling you before, is that the NTDLL loader actually looks up a registry key, image file execution options, and then the file name of the binary you're looking at. And if this registry key is present, you can set certain options like debug flag, stuff like this, which is also very handy for malware analysis sometimes. But in our emulation environment, there's no such specific key there. So we're saying object name could not be resolved. And therefore we just give an error back from our system call, and NTDLL of course expect this, since usually there is no such key, and continues. Okay. So next thing is that it's invoking NT query virtual memory. So it tries to get some self-introspection into the address space that is currently executing, and determining parameters for relocation, stuff like this. And the funny thing is, NTDLL contains a lot of debug strings, debug output, and these are even there in the release builds, but they're disabled by a certain byte, a static byte. And if you just patch this byte to instead from 0 to being any non-zero value, it will output all these debug strings for you. So actually, these debug strings here are not created by me, but they're created by the original NTDLL code, which is very useful for debugging my stuff. So, okay, we don't provide a proper process ID, but yeah, of course we could fix that. There's some random debug output. As you can obviously see, this environment is not 100% accurate either, but that's easy things to fix. So next thing is it invokes anti-open key event. This is like just management stuff it needs for using critical sections later on. It's very nice if you find very little information on these special key events and stuff like this, but it's a very performant implementation for handling critical sections and in case there's no memory, so you don't screw up with like throwing exceptions and so on. It then calls NT-query system information to get various information about the currently running system, like the size of a page in bytes, stuff like this. And what you see here is calls to NT-allocate virtual memory. So, well, this is either already the setting up of the heap or the NT-DLL creating space for some data structures. And this goes on for some stuff, so you have some more initialization of memory and so on. And the next interesting thing is NT-open directory object, where the directory objects are just virtual directories in the kernel's namespace, object namespace. And there's a directory called known DLLs. And this known DLLs thing is basically to both save memory and speed process startup up. So these known DLLs, there's like these DLLs you really see in almost every process, like kernel 32 DLL, user 32 DLL, and so on. And these DLLs, they're actually not mapped for each process at each startup, but instead they will be mapped at system boot time, and yeah, then you just can map the existing section objects into your process. And this has a very nice side effect if you actually care about exploitation. It means that known DLLs are always at the same address. So even with address-based layout randomization enabled, you will always have them at a fixed address. So imagine, for example, a scenario where like you have a vulnerability in some program, that is an information leak, but it will also crash the process. But anyway, if you can somehow restart the process, you can try a second time because the addresses you leaked from these non-DLLs will still be valid, even though ASLR is enabled. So, or if you have like two different processes and you have an information leak vulnerability in the one, and you have a exploitable buffer overflow or whatever in the other one, then the addresses from the one process, at least for known DLLs, will be valid for the other process too. So that's very nice way to circumvent ASLR if you have an information leak vulnerability somehow. Well, of course, that's not the reason why Microsoft implemented it, I guess. But instead, yeah, you save memory because you don't map these images a lot of times, and of course, process startup is faster. And then they will query a symbolic link object, which is the known DLL path. So this whole known DLL stuff is restricted to libraries lying in this certain directory there, so that malware cannot, I don't know, inject its own DLLs or whatever. And then we get some nice debug output actually from NT-DLL new process, image pairs is this, and so on. Current directory is that, and the search path is this. And then it actually calls NT-open file on the directory where it thinks it's the image is lying in, is residing in. So the reason it does this is it actually queries volume information about the volume, which is kind of the disk device or whatever this specific binary is in. And it does that to find out, is this actually a removable media or is it a fixed media? So if you like have execute binaries from a USB stick, it has some safety precautions in case you would just remove the USB stick and whatever. There's some PE flags like only on fixed media and stuff like this too. So that's just for finding out if you're on a removable device or network device for that matter. And does some more memory allocation and so on. Then it calls a different system call to find out the same information again. And you know, like this system call here, system and TFS call. Well, no, this is the first one of those, but yeah, this is to find out if it's actually mounted or not. And then later on, it will do the same thing again with a different system call. So actually in Windows, there's different system calls doing the same stuff, or at least providing overlapping information. Then it tries to access a file, which is an image file name .local. I didn't really investigate what this is. I don't know, maybe somebody else can tell me after this presentation what these .local files are, but it doesn't need these files. Usually you don't have .local files, right? So if it's not there, then it just continues. So we kind of find that file, but yeah, let's continue. So it now calls NT-open section on kernel 32 DLL because kernel 32 DLL is one of these known DLLs. We don't need to actually read it from the disk. and map it into the memory, but it's already in the memory. We just need to add it to the current address space by ntmap open section and then ntmap vo of section. So that basically loads kernel 32 DLL, and we can say successful PE loading and this base address and so on. So let's continue. Okay, so ntdll gives us the debug output. It's loader load DLL is being called, and we're loading kernel 32 DLL from nowhere because it's a no DLL. Maybe there should be some path there, but yeah, maybe not providing enough information. So it opens the section kernel 32 DLL again. No, sorry, I'm screwing up here. So it's now saying loader and TDLL. DLL is used by kernel 32 DLL, so this is where it starts resolving the dependencies of the different files. So it starts snapping imports, basically resolving imports from kernel 32 for kernel 32 DLL, imports from NTDLL. And what it of course has to do is, well, these import sections are usually not mapped writable, so it maps them writable. We'll modify the stuff that are putting the addresses of the imports there and then map them non-writable again. And then it works a very funny system call nt-flush instruction cache, which is a no operation system call on the x86 architecture. But you know, there's different architectures that actually require that cache instructions that require you to do some hardware stuff to flush this instruction cache, like for example ARM. And the system call then flushes these instructions because actually these import tables are usually not only tables of addresses, but instead the compiler will generate jump instructions there, so we have to do this. But it does nothing on the x86 architecture. So then there's some more initialization of the loader, and then here we see that the DLL entry points are going to be called. So it's calling some init routines here, and TDLL has a very, very short init routine itself. That's not very interesting. And then it starts the kernel 32 init routine, which will do a lot of the process environment setup. So kernel 32, it again calls NT-query information process to find out some information about the environment and so on. And in this case, it also asks for the process cookie. So the process cookie is that thing that is used for the heap cookies, for example. It's a random value provided by the operating system through the system call. And well, then it collects some more information and then creates a new section, which is just some memory area it will use for local procedure call communication with the Windows API port. And the Windows API port is part of the common subsystem on Windows. So it's as CSRSS exit process. So this stuff does some tracking of processes. It does terminal windows for you, stuff like this, the console windows, I mean. And then it starts communicating with this. So it queries this object a little bit and does some stuff we don't need really to implement because it doesn't really care about return values. It allocates some more memory, and then actually it calls out by nt request wait rep reports to that local procedure call. So it actually starts communicating with CSRSSX, saying, hello, I'm a new process, and if it's actually a console command line PE binary, it will ask the CSRSS exit to create a new console window for you. So all these console windows from your command line processes, they're actually belonging to the CSRSS process instead of belonging actually to yourself. And then it calls nt-resistor thread terminate port, which means the port will be closed as soon as this thread exits because it's the main thread. But again, I didn't get to implement all these LPC stuff yet. And then, yeah, it queries some more information again. Kernel 32 also parses these image file execution objects, but again, we don't have the specific key here. And then it does some mapping of the NLS sections. This is natural language support. So there's a lot of preloaded stuff for supporting different locales and all processes, and yeah, in this case, I just took the original Windows files too and mapped them on demand there. So it maps these files like Unicode NLS into the process and so on. And then it does nt-query default locale, which is a very obvious thing, but I didn't get to implement that either. Doesn't really need that anyway. And then it starts loading more of these files, locale NLS and sort key NLS and whatever Microsoft uses all these files for. I mean, the benefit of executing all the bytecode is, I mean, it obviously needs those files, but we don't even need to care what it needs these files for because, well, the bytecode that handles this file is there anyway. Then it queries this section and gets some information about these. Then it loads sort tables, some more stuff. And now we're getting to the interesting part because now it allocates some more memory. That's just heap stuff. And then it requests some more CSRSS stuff and waits for the reply. And the problem here is that the whole LPC stuff and the whole CSR implementation stuff is entirely undocumented. So I'll have to reverse CSRSS actually a little bit too. And I didn't get to the part to do all this until now. So as I've said, it's like a Sisyphus tale. But again, for this case, if you just provided some empty return data, it doesn't really complain and care. So, I mean, of course, this adds to detectability, but you don't really need to implement all this stuff. And then we're getting to a funny thing where I'm currently stuck. It actually, the loader, it tries to find one specific address-based query module data, which is there in the kernel 32 DLL I'm using, but it's not finding it, and I didn't debug why it doesn't find it yet. So from here on now, it will fail. It says, okay, I couldn't find this specific API, and then kernel 32 starts to act up, and it says I need this, and so on, and then it basically starts raising errors, and that's as far as I've got. So I didn't even get to the actual original entry point of the binaries yet, because it's so much stuff to implement, but I'm like, this is the last thing that the kernel 32 initialization routine does, so I'm almost there, so to speak. And yeah, I mean, for help of debugging, I have some nice stuff built in here. Actually, it's breakpoint support too, and this is actually what has happened till now. So this memory area here, and this memory here and this memory here is what we initially provided, but all the memory here has been allocated by heap stuff or different other stuff, and then kernel 32 DLL has been loaded and mapped and everything by the bytecode inside, and the CSR stuff gets mapped by some host simulation with the system calls, and that's basically as far as I've got so far. So yeah, that's about it with the demo. So, conclusions and future work about this. You could use this for exploit development because you have very fine-grained but full introspection. It's a fast execution speed. You have some issues with detection even here. It's a lot harder to detect this kind of stuff than the generic AV emulators you see out there. But one of the ways to detect this, for example, would be that you can check return codes. I mean, by definition, there's very few data being leaked from ring 0 to the user land because, yeah, well, this is basically the ring 0 separation. But one register, EAX, of course, contains the return value of system calls, and that's some detectable leaked information too, because we need to provide very accurate return codes, especially in case of error. Well, the real Windows code really just cares about did an error occur or not. By definition, an error is just a value above this constant. But the kernel actually does provide very specific error codes what went wrong. And malware might deliberately cause an error during a system call and might look for specific error codes to be returned. But then again, these error codes could vary across kernel versions and so on, so it's not very reliable for the malware either to do this. And of course, there's side effects on memory buffers that are modified by system calls, again, especially in the error case. For example, you have a lot of APIs that have like a parameter that is the address to a length double word, which is filled with the length of the output data the system call generated. So what does it do in a case of an error? Does it set this length that it would have generated? Well, it actually depends on where in the system call the error occurred. So you need to look at each system call, and there's a way of detecting it. Then sometimes there's system calls that do a lot of things, not only one thing. And if there was an error, should we roll back the things that it already carried out? I mean, the data that it already filled into the buffer, or is it just left in this unfinished state? I mean, by definition, again, all these documentation, or well, that documentation that is on this system call says, in case of error, these buffers are undefined. But of course, there will be some data in there, and this would be another way to detect it. So again, this is a trade-off between detectability and performance. You will never, even with this kind of system call layer emulation, have a 100% accurate Windows environment. because both you probably don't have the time to replace a full Windows kernel development team, and also Windows in some things really behaves strangely in terms of kernel, and there's a lot of system calls. On the other hand, to have a perfect environment, you need like really be running Windows and VMware, and yeah, that's like the trade-off you have to decide. So what's future work about? What could you do? What could be improvements? Well, I always wanted to add some constraints checking, and I did a proof of concept that is based on the SCP constraint solver. So basically, the idea is to interleave static analysis into this dynamic analysis, and look for interesting system calls like reads from the network or checks for date or whatever. Stuff that could be like trigger behavior for malware. And from this point on, do static forward data flow analysis on the usage of these specific values. And then if they're used in conditional jumps, identify interesting values, or if these jumps can never be taken to with a satisfiability checker. For some of these checks, there are better domain-specific ways, like, for example, integer constraints on dates or whatever, but I'm pretty lazy, and the such checkers can handle these cases as well. Not as performant, but they do, so why care? And goals could be, for example, automatic reconstruction of network protocols, like, for example, ISC bots. You want to see the supported commands without ever connecting to a CNC server. Identify specific trigger-based behavior, like, okay, this is a malware sample, but before this specific date, it will not do anything at all. Or identify anti-emulation behavior, like what I've been presenting before. And there's actually from some US university, there's a BitBlaze. There's been a talk about this before yesterday. They kind of do the same thing with all this constraint propagation and everything, but it's not a very well integrated concept at first. So they do a full taint analysis in a real full virtual machine. Then they do the constraint solving on the whole data set, so they have a huge amount of data. Whereas if you would interleave this, as in this proof of concept, which is not really ready for presentation at all, and to leave this into the dynamic analysis, you can just only do forward data flow analysis for very, very specific registers, values, whatever. So you can cut out a lot of stuff you would have otherwise analyzed, which you don't really need at all. So that's something I will be working on too, while I'm also adding all these missing system calls, of course. Yeah, thanks for your attention or in the last slot today. And are there any questions? Yeah, wait for the microphone because.
You mentioned that you're using the LDT. What do you do if the malware code loads the code selector into, say, AX and then tests for the TI bit?
Okay. Yeah, well, as I've said, I'm emulating some instructions in software, like control flow modifying instructions. Of course, all instructions that modify the segment registers or access the segment registers are emulated too in software. So there is software registers. Well, so there's registers. Well, not real registers, but variables where I'm storing the values of these registers that the guest would expect to see. So all these. If there's either a read or a write to one of these registers, it's done entirely in software. Well, I mean, usually you don't see a lot of malware that even touches the segment descriptors or the segment selector registers at all. But of course, you want to support these border cases too, yeah. But it's a little bit slower because it's done in software, but it has not much of a real-world performance impact because little malware doesn't really do that. Okay, any other questions? Okay, well, there's also my contact information if you want to ping me offline or whatever. I'll also be around tonight and for DEF CON. So thanks for your attention.